Chapter 7 Momentum 7.1 Conservation of Momentum. Conserve, in Chinese, 守恒, means the value remains unchanged. You will see very soon that the product of mass and velocity is always conserved in many situations. So, momentum, which is the product of mass and velocity, is always conserved. The words constant and conserve mean two different things. Constant means the same value all the time, such as refractive index, while conserve means the value remains unchanged in the process and usually under certain specific conditions, such as conservation of energy. 1. Velocity, mass, and collision. Experiment 7a is a typical collision. It will show what conservation of momentum means. Let's start the experiment right away.
In this experiment, we will investigate the change in total momentum and kinetic energy in a sticky crash. Mount a motion sensor at one end of a runway. Connect it to a computer via a data logger interface. Adjust the runway for friction compensation. There are Velcro attachments on trolleys A and B, such that they will stick together after collision. Run the data logging program and start data recording. Give trolley A a sharp push to make it move away from the motion sensor and collide with trolley B. The two trolleys then move together. Stop data recording. Try to find out from the graphs the velocities of the trolleys before and after collision. Then repeat the experiment by adding 1 and 2 mass bars to trolley A in turn to double and triple its mass. Find out the total momentum and kinetic energy of the trolleys before and after each collision. What can you observe from the result?
Experiment 7a Trolley crash, sticking together. In this experiment, a moving trolley A collides with a stationary trolley B and then stick together and travels with a common velocity. Just one motion sensor is enough to detect the velocity of A before and after collision. The velocity is positive when the trolley A is leaving the motion sensor and negative if the trolley is moving towards the motion sensor. Reading the velocity time graph is important. You should know how to read from the graph the initial velocity and the final velocity of trolley A. The initial velocity of trolley B was 0, and its final velocity is the same as the final velocity of trolley A. We then calculate the sum of the product of mass and velocity. That means the sum of momentum before collision, which is MAUA, as UB is 0. And we also calculate the sum of momentum after collision, and that is MA plus MB multiplied with their common velocity. Similarly, we can also find the sum of kinetic energy before and after collision. We see that the total momentum of the two trolleys before collision is equal to that after collision. We say that the total momentum is conserved in the collision, while total kinetic energy is not conserved. So the calculation of momentum, which is the product of mass and velocity, is important. Momentum is a vector that has a direction, and its unit is kilogram meter per second. And the total momentum of a system is the sum of all the momenta added by vector addition, similar to the addition of forces. In example 1, the total momentum of Tom and the dog is the vector sum of their individual momentum. So the total is 100 plus negative 80 to the left, which is positive in this case. Momentum is not only conserved in a sticky collision. In experiment 7b, a stationary trolley B is collided by a trolley A again, but in this case, they travel separately after collision. Two motion sensors are necessary to detect the motions of A and B individually. The final velocity of B will appear to be negative after collision in motion graphs, because trolley B moves towards its motion sensor after collision. The rails are also lubricated to minimize friction. The track is set for friction compensation to minimize the effect of friction. In part 2 of the experiment, repelling magnets are attached to the trolleys so that they repel each other when they come close. This further reduces energy loss during collision. Let's take a look of the experiment.
We will investigate the change in total momentum and kinetic energy in a hard crash. Mount a motion sensor at each end of a runway. Connect it to a computer via a data logger interface. Place two trolleys on the runway. Run the data logging program and start data recording. Give trolley A a sharp push to make it collide with trolley B. Stop data recording. Try to find out from the graphs the velocities of the trolleys before and after collision. Then add 1 and 2 mass bars to trolley B in turn to double and triple its mass. Find out the total momentum and kinetic energy of the trolleys before and after each collision. What can you observe from the result?
We will investigate the change in total momentum and kinetic energy in a collision. Mount a motion sensor at each end of a runway and connect it to the computer via a data logger interface. Attach magnets to trolleys A and B so that the trolleys will repel each other when they come close. Run the data logging program and start data recording. Give trolley A a sharp push to make it collide with stationary trolley B. Stop data recording. Try to find out from the graphs the velocities of the trolleys before and after the collision. Then repeat the experiment by adding 1 and 2 mass bars to trolley A in turn to double and triple its mass. Find out the total momentum and kinetic energy of the trolleys before and after each collision. What can you observe from the results?
We can see from the velocity time graphs produced by the data logging system, the final velocity of B appears to be negative, just because trolley B is moving towards the motion sensor on the right. In fact, both trolley A and B moves to the right after collision, so final velocity of B, Vb, should be taken as positive. In this way, we may calculate the total momentum of the two trolleys before and after collision in part 1, as well as in part 2. We may also calculate the kinetic energy before and after collision in part 1 and in part 2. We find that the momentum of the two trolleys before collision always equals to that after collision in part 1, as well as in part 2. But for kinetic energy, it is not conserved in part 1, but only in part 2 when repelling magnets are used, which make it a perfectly elastic collision. To sum up, we see that the total momentum is always conserved in all kinds of collisions. On the other hand, the total kinetic energy is only conserved when the collision is perfectly elastic.